Today he is going to talk about how plasma remnants in an expanding medium from hydrodynamics and holography. Please start.
Thank you. So thanks a lot for the invitation to talk about my work here. And yeah, so the title of the talk is a little bit long and perhaps cryptic, but anyways, the idea is that we have a specific hydrodynamic model which we fit the data from gauge gravity duality, and then we use this hydrodynamic model to analyze this, what we call the hot plasma remnants in an expanding medium due to a phase transition. And well, the basic idea here is my basic idea is to discuss this most recent paper here, which came out like 2-3 months ago. But I will also need to discuss the paper where we actually established this hydrodynamic model, and I will also briefly discuss this letter where we obtained a different result. So the outline of the talk is then as follows. So I will give a lengthy introduction and motivation to the topic of phase transitions, and then I will tell you what is this extended hydrodynamics, how it's set up. And then I discuss briefly this bubble wall velocity result which are from this letter a couple of years ago. And then the main topic of today will be this fourth part of the talk, which are these hot remnants in expanding plasma. And then I will complete. Anyways, I will start with the introduction and motivation. And well, first order phase transition domain walls are fundamental topics in physics. And examples in the context of strongly coupled field theory are, well, in QCD, where we don't really precisely know what is happening, but there is a conjectured phase transition, like deconfinement phase transition at finite density in the QCD phase diagram, which can be brought in heavy ion collisions, maybe at like lower density, but also the phase transition could happen, or several phase transitions could happen at higher densities and could be brought in neutron stars and neutron star mergers. But you can also have phase transitions in strongly coupled extensions of the standard model. So for example, some extensions of the electroweak sector can have first order phase transitions. There could be some hidden sectors also, or some strongly coupled sectors as higher energies than the standard model. And this means that you could have this such a first order phase transition happening through this bubble nucleation in the early universe. And a very basic thing to discuss in the context of first order phase transition is domain walls. So there is some critical temperature of the phase transition, and you can start by looking at static domain walls at the critical temperature. So yeah, so at T equals Tc, the pressures on both sides of the domain wall can be balanced, and the domain wall is static. But if you then go away from T equals Tc, you can have different dynamical situations. You can have nucleated bubbles of stable phase within a supercooled medium, or bubbles of stable phase in overheated medium, or you can also have an interface between phases of different temperatures. And typically in these situations, the phase difference or pressure difference over the domain wall drives the most. So we will have some moving domain walls or expanding or shrinking bubbles. And if you have strong interactions, solving the surface tensor, wall profile, and velocity are all hard questions. So maybe you can use gauge gravity duality. And as for this talk, maybe I should discuss a little bit more about this phase transition happening through bubble nucleation. So you can think of this happening in the early universe, but this is of course more general. So any cooling of matter with first order phase transition will go through something like this. So at the first, you cool down the temperature, and the system, when the temperature goes below the critical temperature, the system is still in the high T phase, but it becomes super cooled. So then you form these bubbles of the low temperature phase through quantum tunneling, and these bubbles expand, collide, and coalesce, eventually filling the whole space. And this kind of process is depicted here from some hydrodynamic simulations in the context of the early universe from this paper. And also, if you are Okay, so if you are in the context of the early universe, you can have gravitational waves generated, first of all, from the collisions of the bubbles, then later also from the sound waves generated by the collisions, which they actually is typically the dominant generation channel, and also later from the turbulence as the plasma settles down. And this may be detectable by observatories, for example, LISA, and maybe it has been already observed by the pulsar arrays because there is some sort of signal which has been observed. And this has been studied a lot by using hydrodynamic simulations. But maybe you can get some additional insights by using gauge gravity duality.
Are you considering some effective action for bubble inclusion?
Well, I will tell you what exactly I will be doing. I won't be considering such a complicated situation like this. I will be considering some much simpler cases. But I will have an effective action, which I will introduce later. And okay, so what do you want to do if you want to do this directly in holography? Well, it's in principle very straightforward. So you can study phase transition and domain walls just through numerical analysis in classical higher dimensional gravity. And well, solving classical actions is in principle straightforward. For example, if you just take the case of planist domain wall, you need to find an interpolating solution between two geometries, which represents two different phases in your theory. Quite in general. However, it's maybe not so simple.
Gauge gravity duality requires a dictionary.
Right.
What is the dictionary for your domain work?
I mean, I here try to be just very generic. I will come to a very specific case later in the talk, where I will show you what is the precise dictionary and what are the example geometries which correspond to the different phases. But there will be an example later. Here, this is just at the general level. You expect to have some two different geometries which are interpolated. I hope that this answers the question. Anyway, so difficulties here are that holographic methods have one coordinate. So if you want to solve something like a domain wall, apart from the field theory coordinates, now you also have a fifth holographic coordinate in your gravity direction. And solving Einstein equations is numerically always a little bit tricky. I mean, it's because I think one of the reasons is because it's not really positive definite problems that you need to solve. And also a specific problem which appears in this phase transitions is typically you would like to study this confinement, deconfinement phase transitions. But then this turns out to be particularly tricky in holography. Because this confining and deconfinement geometries typically have a different structure. This is exactly the kind of example which I will show you later. And this leads to a discontinuity or sort of a topology change in the geometry when you go from the one geometry to the other. And dealing with this is tricky. But so there are different solutions. So you can try to do this analysis in any case just directly in the gauge gravity duality without any approximations. So there are already attempts in the literature, but it's very hard. But then you can also do this you can simplify by forgetting about this deconfinement, proper confinement, deconfinement transition. You can do this kind of phase transitions, which I call deconfinement transitions. This just means that you study phase transition between two geometries which are in the same class. Basically, this just means that you have the geometries on both sides of the transitions are black hole geometries. There's two different classes of black holes. Or then, what I will be using this talk is use sort of effective theory or hydrodynamics. And this kind of effective or hydrodynamic theories have already been addressed in the literature. I mean, there are different simplifications. There's like maybe the simplest thing that you can do from case gravity duality is that you can solve the effective potential for the order parameter of the phase transition by using case gravity duality, and then use this effective potential to do computations in field theory. And this kind of approach has been studied in these papers. But then there is another approach which I will be discussing in this talk, is that I will pick a specific hydrodynamic theory, and I will match the results from gravity simulations of case gravity duality computations with this hydrodynamic theory, so that this pins down what my hydrodynamics theory is, and then I use the hydrodynamic theory to do the numerical evolution. I just forget about the case gravity duality. So at least you get rid of the extra coding. And then there is also a recent paper of mine which I won't be discussing more, but this is like a funny thing. We derived the hydrodynamic theory sort of strictly from the case gravity duality in an expansion motivated by high dynamics of higher dimensional black holes. And I think this approach is, I won't go into any details, but this will be applicable to perhaps to a little bit different classes of theories than the second approach, which I will be discussing in this talk. Anyways, this was the introduction, and then in the rest of the talk, I will be discussing this approach. Or any questions about the setup?
The hydrodynamics is your CFT or?
Well, I will be using a Witten's model, which is well, it starts from like a CFT construction, but you also like you do a compactification which gives rise to a scale.
There will be no conformal symmetry.
There's a remnants of the conformal symmetry. I mean, you introduce a scale through this compactification, which breaks the conformal symmetry. But I mean, you will see. I mean, it is not enough, for example, to change the equation of state from anything to make it different from what you have in conformal theory. So, for example, the equation of state will be just purely conformal. But okay, let me then discuss what are the basic ingredients of this generalized hydrodynamic model I will be using. So this is from this first paper. So the main ingredients is perfect fluid hydrodynamics, which I use to describe deconfined plasma. And then the other ingredients is the order parameter of the phase transition, which I call gamma. And then I use this to describe two phases, sort of follow the large end picture. Yeah, I think I will be discussing this a little bit more later. So okay, what did I say about? Sorry, no. Yeah, sorry, I got confused. Anyways, the deconfined phase, I will normalize my parameter in such a way that the deconfined phase has gamma equals 0. So this means that you have the fluid which is described by the hydrodynamics, whereas the confined phase has gamma equals 1. And this means that the description is such that this gamma equals 1 basically means empty space. So the phase transition just turns off the plasma. This is actually what you expect in young wheels in the large and ceiling.
But there will be some condensate from it.
Condensate?
Yeah, after phase transition. Condensation of your plasma. Yeah, what is it? Plasma. Yeah.
Right. So this is actually one of the main things. I think I will be discussing this a little bit more. So what happens with the plasma? Because I mean, it's actually not really going anywhere. In principle, if you think of young meals, so the plasma should be decaying into glucose, but the number of glucose is much less than. I mean, the number of degrees of freedom for the glucose gas is much less than the number of degrees of freedom in your deconfined gas, and this is particular dynamics for this kind of Young-Mills theory. But maybe this is still a good approximation for like NC equals 3 Young-Mills. If you plot the energy density of NC equals 3 Young-Mills from what you get from the lattice, the energy density really drops very drastically at the phase transition. So it's basically when you go below the critical temperature, all the degrees of freedom are just essentially given. And some key properties of this construction is that the hydrodynamics and the order parameters are coupled in a specific manner, which I will specify in a minute. And this is, as it suggests, that this is directly now defined in the space-time coordinates. So I have like, there is no holography in this description. And I will be mostly actually discussing 2+1 dimensional theory, but you can also do a 3+1 dimensional description. And this is obtained, even though I will be working on the space-time coordinates, the model is obtained by comparing the results from this model to results from a holographic, like a higher dimensional gravity model. I will be discussing this more detail. But yeah, I promise that there will be a like effective action for the hydrodynamic model. And yeah, I mean, this is a possibility on how you can define the model. So you can write down an action. And the action has these 3 terms. So there is one term which models the deconfined phase. So if you only had hydrodynamics, the action would be equal to the pressure. So that would be the description. But now there is also this capital gamma order parameter function. And then there is a confined term, which is just a trivial term. And then I have promoted the order parameter into a dynamical field. And this will be describing what happens at the domain. And the conventions are such that both the capital and small gamma are 0 in the deconfined phase, and capital gamma and small gamma are both 1 and in the confined phase. And the equations of motion are the conservation equation for the energy momentum tensor, and then the equation of motion for the order parameter, which is derived from this action. And this energy momentum tensor is computed from this Lagrangian by following the description of this paper, but this just means that it's the usual hydro T mu nu will multiplied by this factor plus then some mixed contribution arising from this factor, but essentially from the appearance of metric here and the temperature. I'm not going into details about this. And as I said, there's a specific coupling between this gamma field and the hydrodynamics, which arises from this action. And it specifically comes mostly from this term, where you have the pressure coupled to this order parameter. But also in part it comes from these potential, which I will be specifying later. And
So this is 3 or 4 dimension? You said.
Right. So this let's start from the 3-dimensional. So 2 space and 1 time dimension. This is sort of the cleanest comparison we can do. This is basically this comes from the fact that this comes from our choice of the holographic model. Actually,
A gamma, so physical coefficient or just parameter.
Well, this has something to do with the tension of the domain wall, the surface tension. But like, yeah, I mean, there are different choices. I mean, all these functions need to be determined by comparing to these full gravity solutions in a holographic model.
What is your gravity?
I will come to that. Yeah, so this is the next slide. So we will be using this Witten's model. Yes, this is a very well-known example of a holographic theory with a first order confinement deconfinement phase transition. It's the Witten's model. And what we'll be using is, due to simplicity, a lower dimensional variant of the Witten model. The original Witten model is a 6-dimensional construction. I will be using a 5-dimensional variant of this. And well, yeah, okay, I'm not writing the metric here, but it's it's a 5-dimensional gravity solution with one compactified spatial coordinate. And the picture which arises looks like this. At low temperature, the bulk geometry is the one where the circle obtained by compactifying that one of the spatial coordinates closes off into a cigar in the bulk. So this is what I denoted like here. So okay, so you are going to finite temperature. So this means that you also compactified the Euclidean time in the system. So then you have two compactified coordinates. So you have the Euclidean time and you have this extra spatial coordinate which has been compactified. And then you have these two symmetric solutions. In the low temperature deconfined phase, this geometry is such that the work factor of the geometry related to this phi coordinate has a Lagrange factor which is such that the geometry in this sector corresponds to this cigar-like geometry which ends smoothly at some value of the bulk coordinate when you go away from the bulk. Whereas nothing is happening when you change the time direction. So this is or when you go towards the bulk for the geometry in the time sector.
You are drawing metric here. This is represent metric.
Yeah, this represents the geometry. Yeah, I could also write them the expression for the geometry. In the 5-dimensional case, it's just let me try not to screw this up. So this is the like confined case, low temperature phase. The blackening factor is here. That is F. So this is some non-trivial function. I don't know if I recall correctly, but if you write it like this, then I think it's like yeah. Here use the U coordinate, but here I'm using the R coordinate. So this is actually the R coordinate is the inverse of U. And if you go to the black hole geometry, is otherwise similar, except that the blackening factor is just here in front of the time direction rather than this compactified. Compactified spatial direction.
This is Einstein gravity plus some scalar field or?
Right. Yeah. So this is just a solution to 5D Einstein gravity with cosmological constant.
Oh.
This is the like ADS Schwarzschild black hole, and this is the like analog but with a compactified one compactified spatial coordinate. Right. So there are these two geometries which are sort of symmetric with respect to change in the time and the space compactified spatial direction.
U lambda is related to I star.
Sorry?
You have U lambda.
Right. So the U lambda. So there is there is this parameter here, and in principle, the different geometries would have you should say that the U lambda is perhaps the parameter in this geometry, whereas this UT is the parameter in this other geometry. In principle, they could be different, and only this parameter, this is the black hole geometry, is really related to the temperature. So you could imagine that you keep this geometry fixed. This U lambda is just gives you the scale of confinement, and you change the temperature, and then the blackening factor here changes. And then there's a phase transition at the exact point where these functions actually become identical. So where it's the symmetric point where the geometries are actually fully symmetric with respect to the change of the points. So this is the Hawking page phase transition which happens in this system. So anyways, there are these two different geometries, and you can have a first order phase transition in between them as the temperature varies. I hope that it's not too confusing. I feel like I sort of made it into a mess. But the thing is that since there is a first order phase transition, there is also a domain wall solution, and it has been constructed in the literature. So these people already 20 years ago constructed numerically the static static planar domain wall solution interpolating between confined and deconfined phases. And this is a highly non-trivial geometry because there is a topologic says here due to the fact that the rho of the cigar and the cylinder here are integers. And the structure of the geometry, you can choose your coordinates in such a way that the geometry is, the two-dimensional slice of the geometry looks like this, where the two-dimensional slice are the coordinates which are relevant here is the spatial coordinates, which takes you over the domain wall, and then the holographic coordinate. So the holographic coordinate here goes in this direction, sort of a radial direction, whereas this spatial coordinate goes in this direction, in this construction. And the solution, this ADS Soliton solution, what they call the ADS Soliton solution is the solution of the low temperature phase or the Soliton phase where you have a cigar in the compactified spatial direction, whereas this is the black hole solution is here. So in this direction and in this direction, you asymptotically approach the geometries of the two different phases, whereas this region here in the middle, this is the domain wall region. So they have this very complicated solution, but after you have solved it, you know it, and you can use the holographic dictionary. It's very well known in this stage to compute observable. And we use the solution with this 5-dimensional solution, which I wrote here explicitly, which is due to a 3+1 dimensional boundary theory with one compactified coordinate. So this means that there is really non-trivial or like a Minkowski space structure in 2+1 dimensions, and then this one compactified coordinate is just sort of integrated over. But okay, so what you can get from this solution? The basic observable that you can compute when you have a geometry is the energy momentum tensor of the field theory. And this is, well, you can take the solution and extract the energy momentum tensor. And here I plot a specific combination of the energy momentum tensor in the time and in this compactified space direction. And the understanding here is that you can, well, I have normalized in such a way that it goes from 0 to 1, but this essentially characterizes the variation of the energy density when you go from one side of the domain wall to the other. And it turns out that you can get an extremely good fit to this data by this simple hyperbolic time answers. And this essentially maps this quantity in the extended hydrodynamic model. But this is not the only data that you can get from the gravity solution. There is a little bit more information. You can also study the energy momentum tensor in the direction parallel to the wall. And this has this light bump. And the normalization is such that you should compare the bump to this one. So this is a smaller feature, but you can also be fitted. It can also be fitted with like simple ansatz. And in the hydrodynamic model, as it turns out, if you compare what the energy momentum tensor in that case is, this maps to the gamma prime squared. If you recall, that's sort of natural because I told you that the gamma prime squared comes from here, and this is what it should be describing the domain wall. And yeah, indeed, this, as you can show, this bump here is related to the surface tension at the domain. But by the way, you can also show that this the tangent fit works well in other holographic models, for example, some non-conformal Einstein-Maxwell-Dilaton models. But it's this is sort of a particularly nice example. I mean, you cannot really see the data, and I got here both the data and my fits, but you cannot see the two curves separately because they are so close. And then what you can do is that you can take this action and try to reproduce these nice fits. And here, the first step is that we set this potential for the order parameter to have this double well structure. And this is basically required to obtain this hyperbolic tangent profile for the, as a solution of the equation of motion for gamma. And simultaneous match with this bump in this TYY can be obtained if we, for example, make this kind of choice for this capital gamma and small gamma relation here, and set this A factor just to a constant. What you really would like to do is that you would like to identify capital gamma directly with small gamma and set this to constant. So this would be the sort of an ideal model. But this doesn't really, it turns out that this doesn't really work. This would give you sort of the scales of the scale of this domain wall and the scale of this bump would be quite drastically different, so that they like could fit what would not be possible. So you need to do something more complicated than that. And this is one possibility. And there is another possibility. Actually, if you require that these two fields are the same, then it turns out that you can get a good fit if you choose this A function to be of this form. But this turns out to lead to problematic similarity that gamma equals 0 and gamma equals 1. And this is not, if you just consider static solutions, this is not a problem. But then when you try to do dynamics with the system, having this kind of structure in the Lagrangian turns out to be tricky. So we won't be using this choice in this in the following, but I will only be using this one. And okay, I also introduce here this beta, so the temperature dependence of the potential. And as then you can use this beta to fine-tune your fits to the data. So here again, I saw both our fit and the data, but you cannot see separate curves because they are all on top of each other. And well, it turns out that for this specific choice of beta, that it is very good.
So beta equal 2 plus 2 gamma, all okay for these two possibilities?
Yes, both of them. But I will be only using this. And also, as it turns out, this choice of gamma here is sort of a natural also in the sense that if you now plug this in here, and you also see that then you have a polynomial dependence on gamma here, and the pressure, well, yeah, I didn't write here, but the pressure we take to be just conformal d to the fourth, maybe it says some other choice. So if then this the gamma dependence here and the potential here, you recall that this was also sent to a constant, they combine nicely to a temperature-dependent effective potential, which has this like an expected structure that you start at critical temperature, you just have a regular double well, and then when you go to a temperature which is different from critical temperature, then you create an imbalance between the vacuum. Okay, that's everything I wanted to say about the setup. I hope that is more or less clear, and then I will go and discuss applications. And the first application that I want to discuss briefly is the application to bubble wall velocity. You notice that I'm using quite a bit of time already. So, okay, so what do you expect? If you take a domain wall and put the system at temperature which is higher than the critical temperature, you expect that the domain wall starts moving. First it accelerates and later propagates at constant velocity. And you expect also that this velocity somehow depends on some friction, which is hard to compute. So, okay, this is one of the first things that we did with this model fitted to Witten's model, right? The hydro model fitted to Witten's model. And the results look like this. So this is as a function of the time and spatial coordinate, one of the spatial coordinates. And well, this looks somewhat more complicated than the simple picture that you have in mind. So this was quite a surprise for us. Maybe if you were like a real hydro expert, this would not be so surprising. But so what is going on? It turns out that anyways that the picture is not so complicated. So if you look at these plots, indeed the domain wall is moving right, and it's to right, and it's going at roughly constant speed as expected. But also there is this hydrodynamic wave moving to the left, and the hydrodynamic wave is this picture here. What you can see also from these plots is that there is pressure difference essentially only over this hydrodynamic wave. There's no pressure difference over the domain. The domain wall is basically just force. And between these two walls, there is plasma moving to the right, following the domain wall. And because of this simple picture, as it turns out, you can just determine the wall velocity by integrating the equation of state over this hydrodynamic wave. And this is simple because now you're actually only working in the deconfined phase. So your order parameter is set to 0, and it's just perfect fluid hydrodynamics. And you can actually go to Landau Lifshitz, and this hydro wave is solved there, and you can get a surprisingly simple formula for the domain wall. And then you can actually, what we did was that we also did gravity simulations. And these gravity simulations we actually did in a simple, we didn't do them in a Witten's model because that would be difficult. We took a simpler case, which is some like 5D Einstein-Dilaton gravity. Anyways, we set up it in a way that should give a relatively similar physics. And indeed, in here I brought the pressure as a function of the position and time again, and you see that the pictures are very similar, apart from some wiggles here in the Witten model, which might be due to the fact that there's no dissipation in our perfect fluid model, whereas in the full gravity simulation there is. And you can actually then compare these wall velocities from this. We actually took them from this gravity simulation. So these red dots, and we can compare them directly to the results obtained from this formula, this blue curve. And there is a very nice match. And by the way, you can also get a very nice match at bubble nucleation at T less than Tc, but I won't be discussing that here.
Can you also say something for hydrodynamic wave velocity?
It's the same.
Same.
It's the same. You know, you can see it from here. Sorry. I mean, the plasma velocity is just constant everywhere. But the movement of the wave actually, it's just moves at the speed of sound. Yeah, so better not get confused. anyways, this is everything I wanted to say about the result for the bubble ball velocity, and then I will go to this more extensive topic, which is this hot remnants in expanding plasma. Right. So studying expanding plasmas is phenomenologically motivated. Well, there is the pure expansion after heavy ion collisions, or then matter expanding in the universe. And we use this Friedman of Professor Volker to describe this. And what we are focusing is that we focus on these remnants of deconfined matter. So this is the last stage of a deconfinement transition in an expanding setup, where most of the space is already in the confined phase, but you have some remaining parts still in the deconfined phase. And okay, so this is the thing which I already briefly explained. There was a question. So there is this specific Larsen feature in Young, which indicates that the decay of these remaining plasma poles should be slow. So in the deconfined phase, the energy density is high, NC squared, but in the confined phase is NC to the 0, essentially just 0. So consequently, by conservation of the energy, these deconfined resonance really don't want to decay. Their decay rate is 1 over NC suppressed, or actually 1 over NC squared suppressed. So, and maybe this is already also a good appreciation actually for NC equals 3 Youngins. But okay, so what we will be doing is that we use again this extended hydrodynamic model fitted to this 5D Wittens model. So we start with this variant fitted to the 5D model, which means that you have 2 plus 1 dimensional Minkowski space plus 1 compactified direction. And we restrict to planar configuration, which depend on only 1 spatial coordinate. And we start with a setup which corresponds to a plasma in a Bjorken expansion. So we write a metric like this, where this tau is the proper time and y is the pseudo rapidity. So an expansion implies cooling. So for example, for conformal fluids, in this setup, you could get this result that the temperature goes as the 1 over the cubic root of tau. And planar configurations in this case means that you have configurations which only depend on this proper time and x. And what we want to do is that we want to study these deconfined blobs. And you can sort of generate them from the start. So you can start from a completely deconfined phase, and you can generate this deconfined blob by inserting 2 Gaussian perturbations in the initial state at some locations, which then this perturbation gives rise to tunneling of the system to a confined phase. So this contour plot here shows the value of this gamma field. So gamma equals 1 is confined and gamma equals 0 is deconfined. These red regions here are confined. So therefore you get this deconfined blob here trapped between 2 confined regions, which expand rapidly because the system cools and this deconfined plasma is actually unstable. But this blob this cannot decay because of this energy conservation. So there's nothing it could decay into. And you can then study this blob here in the middle more precisely. And what we did was that we actually did a separate simulations where we took a larger blob and we just started from rest, the system cooled down, and we see what happens. And near the edges, you have a picture which is actually similar to this to the results that we obtained in this letter. So you have this. So okay, I'm showing here that at an initial state of time, or at an early stage of time, the profile of the energy density as a function of x. That these are the domain walls, but there are also this other feature here, and these are actually the hydro waves which are going in towards the center of the bubble. So there are these hydro waves. And if you look at, okay, so this gray area here shows where the bubble is. And here, I'm showing the temperature as the blue curve in the center of the bubble, and as this, the orange curve is the temperature here in the edge of the bubble. And in the middle, the temperature first decays because of the expansion of the space, but then eventually you will get hit by these hydro waves, and this, after the hydro waves pass, the temperature goes up around at DC or around. Actually, at these edges of the block, it's already at very early times, it's already at around T equals TC. So these hydro waves sort of heat up the whole bubble to a temperature which is around the critical temperature. But then this is sort of the very early time picture of what is happening. Then you can look at the evolution at later times and see how this remnant eventually decays. The simulation shows that there are two stages. Initially, the blob just shrinks in a way which is consistent with energy conservation. And this means that the width of the blob decays as the inverse of time, of the proper time. And in this phase, the temperature is just close to the critical temperature. So this is not surprising. This is what you would expect for like a phase transition that proceeds slowly. It equilibrates at the critical temperature. But then you get into a different phase where this gamma field, which I'm plotting here as a function of x and the proper time, starts to increase in the middle of the block, away from the zero value of the deconfined plasma. And this phase starts when the size of the block is comparable to the size of, to the width of the domain wall in the system. And you can look at this in more detail. Also, the shape of the order parameter freezes in this phase. So I'm here plotting it at different times. So actually, what you need to do is, what I mean is that, okay, so the order parameter is approaching 1 slowly, the value of the confined phase. But so it's very different from 1 normalized to the maximum. This has always, or this has this sort of similar shape at different times. But there is another, so this is a peculiar feature of the block at late times, but there is another feature which is perhaps even more surprising, is that as it turns out, temperature in this last phase starts to increase well above the critical temperature. And this is why we call them like hot remnants. So this is what I'm showing here. So in the last stage, so this is actually a simulation which is a little bit smaller block, and then running to later times so that you see this increase of the temperature more clear. So the blue is our simulation result, and it's clearly going up above the critical temperature. But as it turns out, this can be understood in rather simple terms. Namely, you can look at the virial theorem. So the virial theorem, based on our action, tells you that this gamma prime squares would equal the total effective potential of the system, which is defined like this. Apart from the potential that we plug in the action, there is also this coupling term coming from the coupling to the order parameter to the hydrogen. And okay, this formula perhaps doesn't tell you much, but you can just plot what this effective potential looks like. And it has this expected double well behavior, which, well, where you have create this imbalance between the confined and deconfined vacua, depending on which temperature you choose. And we see that in the middle of the block, well, in the middle of the block, because of symmetry, gamma prime must equal to 0. It's I mean, you expect that it's sort of an even function of x. And the value which you could call gamma star. So this we already saw from the simulations that the value of gamma is increasing towards 1 here in the middle. And if you plot gamma prime equals 0 in this virial theorem, it just means that the total effective potential must vanish at gamma star. So what does this mean? So this means that the point where the total potential vanishes must increase. Well, starting from 0, it must start and increase towards gamma equals 1. And if you look at these curves, the temperature at which the 0 of the effective potential moves to the correct direction is above the critical temperature. So this is consistent with the qualitatively what we expect, and you can actually go and solve this equation and plot the temperature that you get, and this is this orange curve here, and it matches precisely with the simulation results. And notice that this is very general argument. I mean, I'm just using the virial theorem and the effective potential. So even though it's coming from this complicated simulation, the argument itself is very simple. It looks like it's much more general than our simulation.
But there is also decreasing gamma star.
Right. So the gamma star decrease. Gamma star.
You have 2 zeros.
You mean this?
Yeah.
You said that this would be a possibility, right? But that's not seen in the simulation. In the simulations, I mean, that's also what you expect to be the physically reasonable solution. So the gamma must somehow, it must in the end up here because of the expansion pumps in the end pumps out all the energy of the system. You must end up in the true vacuum of the system, which is the confined phase. That's how you should where you should get it. And okay, but apart from the temperature dependence, you can also roughly understand the shape of the freezing of this gamma field at late time. So we use this virial theorem with this approximation of the potential. Okay, I mean, this is basically the expansion of the potential around gamma equals 1. And if you really do the expansion carefully, it's actually analytic. So this could be a linear term. But the square root term here sort of captures nicely also like the higher order corrections of the potential. So this is, overall, this is a nice or reasonable approximation to the total potential. And if you just plug this into the virial theorem and solve, you get this solution. And this is actually this red dot dashed curve here, which fits the profile quite well. And this beta parameter here, we find this roughly decays as the inverse of the square root of small. Okay. And the last thing which I want to discuss is that now we have demonstrated the behavior of the hot remnants in this Jarvinen expanding plasma. But we expect that this finding is generalized to also other expanding cells. And the natural geometry to check is the RW metric. And for concreteness, we take it to be the radiation dominated metric. So AT is the square root of T. And okay, but now in order to do this properly, we need to generalize our model to this 3 plus 1 dimensional plus 1 compacted 5 dimensional case. So we need to add one more dimension in this setup. So this means that these should be really using the 6-dimensional Witten models. But okay, this would mean that the pressure would be T to the 4 instead of, sorry, T to the 5 instead of T to the 4. And well, this is not phenomenologically reasonable. So we choose to keep anyways this P equals T to the 4. and also motivated by the fit to this energy momentum tensor throughout like 6-dimensional variant of the Witten model. We keep this gamma, the relation between the two gammas to be the same, but we modify the temperature dependence in the potential in such a way that instead of this beta equals 2 plus 2 gamma, we just set beta equals 4. So this is motivated by the 6-dimensional fit, which I'm not going into. And it's also like a slightly simpler choice than this 2 plus 2 gamma. But this is a little bit more phenomenologically constructed model than the 2 plus 1 dimensional case. But it's anyways coming from the fit and phenomenology. And then we apply, so again, we consider just planar deconfining domains. So we only consider configurations which depend on the time and one of the spatial coordinates. And then we just repeat the same study. So you start from some large deconfined blob and let the system expand and cool down, and you study the decay of this deconfined blob. And you observe the same two-stage decay as before. You first see a shrinking, and in the shrinking stage, the width of this deconfined blob behaves like this, and this is consistent with energy conservation. And when the blob becomes of the size of the domain wall, you have this consequent decay of gamma heating up. And they are again described the virial theorem, except that now you need to modify your virial theorem by plugging in this factor of 18. It just comes from the metric. And again, you can study the temperature in the middle of the blob with this blue curve here. And what is given by the virial theorem with our model is this orange curve, and it's again perfect. So this is everything I want to cover. So then I will go to the conclusion. So the model I was discussing was this extended hydrodynamic setup with perfect fluid hydrodynamics coupled to the order parameter in a specific manner. And this was fitted to data from this holographic fittance model. And the first application which I discussed was this simple formula for domain wall velocity, which was motivated by our simulations. But the main part of our talk, today was this description of this hot remnant in expanding space. So what we did, we studied these slowly evolving deconfined blobs formed in a phase transition. And we identified it like two stages in at late time, this shrinking of the deconfined blobs and then subsequent decay towards the confined vacuum. And interestingly and surprisingly, we found this that these bubbles start heating up in this last stage. And we understood this behavior anyways by using virial theorem and simple description by using the sort of effective potential of the system. And then future directions. So we would also like to do remnants in medium with faster expansion, because all these simulations I showed you, the expansion was relatively slow. So there was nothing really drastic dynamics going on. This was because if you want to do anything which is fast, our like this simple hydro code which I have written, you cannot tolerate that. It will immediately crash. So maybe for this we need to do something with our code first, and then a potential important addition would be the addition of some global components. So you would actually add some matter also in the confined phase, because this would allow you to describe really like also the decay of the deconfined matter into some like confined component of matter. And then it remains to be seen how this affects these hot remnants. And of course, you can study more complicated setups like with cylindrical and spherical forms. This is actually what we are doing at the moment. And eventually you would like to do like more complicated things like bubble collisions and gravitational wave production, but this is probably like far future at this point. Thank you for your attention.
Exactly 1 hour. Any questions? I have one question. So I'm not familiar with the hydrodynamics, but I remember some stage of the hydrodynamics engaging gravitability. People consider some shear viscosity and something like that.
Yes.
In your hydrodynamic model, isn't there that concept?
No, I mean, we use perfect fluid hydrodynamics, which which means that there is no viscosity. But you might think that maybe this is not so not a good approximation, but well, actually, maybe I should point out here. Anyways, like this formula for the say the domain wall velocity. So this is just coming from a perfect fluid hydrodynamics computation. Whereas this holographic computation that we are comparing to, this is a dissipative computation. So this does include this viscosity. And despite this, we get a good agreement. So maybe using perfect fluid hydrodynamics is not such a crazy idea. But eventually, maybe you would also like to think how to add viscosities in the setup. I didn't put it in my future directions, but maybe this is another thing to look at.
Yeah, other questions.
So the holography is about Newton's law.
Right. I mean,
You didn't explain much today.
Yeah, I mean, I didn't tell you much about the Witten's model because basically we just need the team rule. Then you use that to fit the potential zero hydro model, and then you do dynamics. In principle, you could also use some other holographic models.
But are these two anyway, I mean, consistent with any experiment, real observation?
The Witten's model.
And as well as your, what they agree.
Well, Witten's model is a rather rough model for Young-Mills theory, in the sense that the equation of state is, well, it's this in the confined phase, and then it's just so this is the confined phase, and then it just in the deconfined phase is this, and in the confined phase this is just constant. Well, which you know, in my normalization is such that the constant is 1. But the critical temperature is also 1. That's where the pressures are. So okay, this is not a good. As for the equation of state, this is not a good model for the Young-Mills. You can do like a different holographic model which reproduce the equation of state. Maybe there, but then it's not like. I mean, this is a top-down construction. In principle, Witten's model is top-down construction. So the string theorists usually like it more, but if for phenomenology you would like to do something more complicated.
What is the experimental behavior?
Right. So, like lattice result for Young-Mills, say P over T to the 4, it looks something like this. So it's very small, and then it grows at starts to grow at T equals TC.
It's growing.
Yeah. And okay, for the Witten's model, yeah, okay, well, it would be like just something like, I don't know, something like that.
The other way, no?
I'm normalizing by T to the 4 here.
Right, okay. Goes to 0.
Yeah, maybe you should actually, maybe you should subtract. I think in order to do an honest comparison, you should subtract this, or plot the difference between the deconfined and confined phase, and then I don't know how the plot would look like, because then you have -1 here, and this should be 0. You can do the plot, but it doesn't look like it's. I don't think it's very close to the data. Maybe not crazy, but.
Do you think your model will give some insight to black hole physics?
So this is because in principle, yeah, there has been discussion. So what does this actually mean? This decay of the setup, because the holographic description would be that, yeah, well, this part is a black hole, and okay, the other part, if you are in the Witten's model, that's the solid geometry. So then this would be like a shrinking black hole, which eventually sort of decays. So this is sort of like a decay of the black hole. But from this, it's maybe not so straightforward to see how what happens in the geometry. We also don't know how like faithful description of this is to what you would get if you were able to do this kind of computation directly in the Witten's model. It's quite complicated.